In this film, we're going to look at different kinds of electromagnetic radiation and see some of their uses. We shall look at parts of the electromagnetic spectrum. Here's a light source. It's actually a xenon discharge lamp. We're going to use it to produce a spectrum. There's the light, a condensing lens, and a hollow glass prism which contains a liquid called carbon disulfide. The prism disperses the white light into its separate wavelengths, producing a visible spectrum on the screen. Red on the left, then the wavelengths getting smaller as we pass to blue-violet on the right. If we pass an electrical discharge through mercury vapor, a lot of radiation with a wavelength less than the wavelength of blue light is produced. It's part of the invisible spectrum below the blue, which stretches away beyond this end of the visible spectrum. It starts about here. It's called ultraviolet radiation, and you can't see it. We can only see here the blue light also produced by the discharge tube. But if ultraviolet, UV, radiation falls on certain substances called phosphors, it's absorbed, and its energy is turned into visible light of longer wavelength, which of course we can see. This is how the fluorescent tubes work, which are so often used to provide illumination in the home and in industry, like the control room of this power station. Just beyond the other end of the visible spectrum, there's another kind of invisible radiation with a longer wavelength than the visible red. We can use this detector to pick it up. It's called infrared radiation, and when it falls on the detector, it will cause a small electric current to flow. Nothing happens in the visible part of the spectrum, but when we reach here, just outside the red, look, a current passes. Go further, and the current falls. The peak of this invisible infrared radiation is here. It's electromagnetic radiation, just like visible light, but it's got a longer wavelength and we can't see it. Let's go back for a moment to ordinary visible light. These three lasers are aimed at a large concave mirror at the other end of a long box, which can be filled with smoke. Turn out the lights and switch on the laser beams. When they hit the concave mirror, they're reflected like this to meet at the focus of the mirror on the right. You'll have seen ray diagrams like this in books. The reflection of light at a concave mirror. Now we're going to show that infrared radiation behaves in exactly the same way. The electrical radiant heater element on the right takes the place of the lasers, and there's a parabolic mirror. Infrared radiation streams off from the heater onto the mirror and is reflected to the mirror's focus, where there's the head of a live match. After the heater's been on a short time, let's watch it again. Reflected infrared radiation is being concentrated by the mirror onto the head of the match. We can prove that it's radiation reflected from the mirror which is igniting the match by putting this mask, black on one side and shiny on the other, between match and mirror. Nothing happens until the mask's moved away. Infrared radiation behaves like visible light because it's part of the same electromagnetic spectrum. This is the focal point of a different kind of concave mirror, designed to bring to focus electromagnetic radiation of even longer wavelength than infrared. It's a radio telescope picking up radiation, short radio waves, sent out by the stars. We're going to aim it at the sun. We can't see the sun on this overcast morning, but the radio waves coming from it will be reflected by the dish of the telescope onto the aerial at its focus, and our instruments will tell us when this is happening. We're coming onto it now. Here's the peak signal coming up as the telescope points directly at the invisible sun. Then it falls again as the dish moves off target. Radio waves form yet another part of the electromagnetic spectrum, behaving in many ways like the light waves we're all familiar with. It's just their different, longer wavelength which distinguishes them from infrared and visible light. Here at Jodrell Bank in Cheshire, there are far bigger radio telescopes than the one we've just seen in action. Radio waves, like infrared, behave in many ways as visible light does, because they're part of the electromagnetic spectrum. This giant dish is simply an enormous mirror, gathering radio waves from stars in outer space, or signals from man-made satellites when it's tracking a space shot, and reflecting them onto a detector as its focus. Radio telescopes are used to investigate processes going on in distant parts of the universe. They've given astronomers information which they could never have obtained using optical telescopes, although both visible light and radio waves belong to the same continuous spectrum of electromagnetic radiation. Here's a demonstration which shows that the short-wave radio waves, called microwaves, do have some of the same properties as visible light. A laser again, shining through a milky fluid to show up the beam, with a glass prism in the center. You all know that a prism refracts light. Here you can see this actually happening. Can we refract microwaves, short-wave radio waves? On the right, there's a microwave transmitter, beamed at a microwave receiver in line with it, with a meter on the left. Switch on, and the deflection of the needle shows that microwaves are reaching the receiver. They can be blocked off quite easily. Watch. These are 2.8 centimeter waves, but you can find out all the wavelengths of the different kinds of radiation for yourselves afterwards. If we now move the detector round, like this, the microwaves no longer hit the target, as the galvanometer needle shows. Back into line again, and the detector picks up the microwaves. This prism contains liquid paraffin, which does not absorb microwaves. They pass through it, but they're refracted. Their path is bent, as you can see. The detector has to be moved round to pick them up. This is exactly the same effect that we saw with visible light. Here's something else we can demonstrate. We swivel the prism round to a different position, like this. Now we've got to bring the detector round until it's at a right angle to the transmitter to pick up the microwave signal. There. Here's the plan view, with the transmitter on the right and the detector bottom left. The microwaves are being reflected from the inner face of the prism, like this. We call this total internal reflection. And if you look at the prism, you can see a reflection of the transmitter. Light is undergoing the same total internal reflection. Both visible light waves and invisible microwaves are being reflected from the inside face of the prism. They're behaving in the same way, because they're both part of the electromagnetic spectrum. Here's an important application of the total internal reflection of light. This is a light source. If we plug in this flexible tubing, look, light comes out at the end. The light has somehow gone round all the corners to emerge at the end. If we look at the end, we see that there's a bundle of fine glass fibers. Light passes along each fiber, undergoing total internal reflection, like this. There's actually a bundle of such fibers, and they're covered round the outside with black plastic. Here's a medical instrument which makes use of fiber optics, as it's called. Light passes down a set of fibers around the outside, leaving fibers in the middle to carry back an image of whatever the probe is looking at. This lady's larynx is being examined. The probe's passed up her nose and down into her throat. The doctor can move it around and get good, clear views. These are her vocal cords. Vibration of these produces the sounds of speech. Looking further down towards the entrances to her lungs. Using instruments like this, many different parts of the body can be examined. A brief glimpse of the vocal cords again. This is a very exciting view. Those rings are muscle. The total internal reflection of light in those bundles of glass fibers being applied in medicine to find out if anything's wrong. Another application of reflection, this time of short radio waves, microwaves, at a television station. At the top of this mast, there's an aerial to receive shortwave transmissions from outside broadcast units. The waves are channeled down from the top by wave guides. Here's a short section of one. It's made of metal and it's hollow, with polished inside surfaces, as you can see. There's a long, straight waveguide passing up the mast. The microwaves are kept traveling down inside the waveguides by internal reflection. They can be carried around corners by units like this. They pass round the corner, reflected from inside face to inside face. And this section can be bent to fit any required path. A simple physics principle again, applied to broadcasting. Another example. We're going to use a microwave oven to heat up the 200 milliliters of water in this beaker. The probe tells us that it's at present at 18 degrees C. Into the oven, and we switch on and start a stop clock. While the water's being heated in the oven, let's look inside one of these microwave ovens. There's a microwave generator at the back, and the microwaves, which have a wavelength of 12.2 centimeters, are carried inside waveguides to the inside. Internal reflection again. You can see the two slots by which the microwaves enter the oven. There and there. This arrangement would simply direct two microwave beams downwards to the floor of the oven. So this thing, like a fan, is used. The revolving blades act as mirrors, scattering the microwaves throughout the interior of the oven, so that they're absorbed by the things we wish to cook, or just heat up, wherever these are in the oven. That water's now boiling. After 1 minute, 11 seconds, we take it out. And you can see what's happened. The water's absorbed the microwaves, and their energy has been converted into heat, which is how microwave ovens work. To finish with, let's look at more electromagnetic radiation with a lower wavelength than light, beyond the blue-violet end of the visible spectrum, and beyond even the ultraviolet. This is a simple X-ray tube. It's connected to the high-voltage leads from an induction coil. There's gas at very low pressure inside the glass tube. When the high voltage is applied, electrons stream off from this negative electrode, the cathode. When they hit this positive electrode, an anode, X radiation is produced. It streams off from this anode. When we switch on and put the lights out, we can see a dim blue glow. Some light is produced, but we can't see the X-rays. They're part of the electromagnetic spectrum, with wavelengths much, much smaller than those of visible light. X-rays can damage living things, so we put a lead shield in front of the X-ray tube with a circular aperture to let through a beam of radiation. This is a fluorescent screen. When X-rays strike it, they produce light on the screen. We put it in front of the aperture. Now for a demonstration. A cardboard box will be almost transparent to X-rays. They'll pass right through it. But these metal pliers will stop the X-rays. We place the box between the X-ray tube and the fluorescent screen. And there's a shadow of the pliers, thrown by the X-rays on the fluorescent screen, and you can just see the edge of the box. X-rays are of course used a lot in medicine. This girl is having an X-ray picture taken in hospital. A photographic plate is placed beneath the bed she's lying on, and her position is arranged so that the X-ray tube will send a beam of X-rays through her onto the plate. Now, a short dose of X-rays will do no harm to the patient, but the radiographer works in here for long periods, so she operates the equipment from behind a shield. Otherwise, she'd be exposed to X-rays every single time she dealt with a patient, which could harm her. Now a picture at this angle.
We breathe in now, and right out, and stop. Don't breathe. Breathe normally. Pretend to lie on your right side.
When the plates are developed, we get results like this one. It's a negative, by the way. Bones are opaque to X-rays, they stop them, so we can see the ribs quite clearly and part of the spine. Other parts show up too. Here's the diaphragm and the outline of the heart.
Morning, Miss Moonen. How are you? Now,
This radiologist is going to X-ray the girl's stomach. Now, the stomach is transparent to X-rays, so she has to drink a liquid containing a substance called barium sulfate, which is opaque to X-rays. This will coat the inside of her stomach for a time, and the radiologist will be able to get outline pictures of it and see if there's anything wrong. He has to stay in the room whenever he does such examinations, so he wears a very heavy apron containing lead to shield him, or he'll get a dangerous dose of X-rays over the years. Here comes the barium drink.
turn a little bit away from me. A bit more, turn your feet. That's it, stay like that. You can see yourself in that monitor up there if you want to. Right, now, start drinking now, please.
Watch it go down when she swallows. And again.
That's fine.
Here's the stomach filling up.
Right, that's all for now. Just keep quite still and we'll bring...
X-rays, like the ultraviolet, infrared, microwave and radio waves, are in the great continuous series of which the visible spectrum forms only a small part. These are all forms of electromagnetic radiation, some properties of which we've looked at in this film.